In this question from Winter 14, paper 4.1, we are going to derive some equations surrounding energies when you have a satellite that is in orbit. Okay, so there's a little bit touch of orbital mechanics. All right, so sometimes if you have watched the previous example, you will see, oh, the rocket is approaching the Earth or traveling away from the Earth, or the rock is coming towards the Earth. All these things are not in orbit. They are not around the Earth. They're just coming towards or going away. But what happens if, let's say, we achieve a stable orbit? Like, for example, here, you can see there is a satellite, right? The satellite is just, chilling in its orbit. Do you know that planet Earth, we have a lot of satellite? We use it for internet. We use it to watch our favorite football match in the UK. We use it to stream physics lectures because it's the pandemic, etc., etc. Okay? So satellites are in stable orbit. Once we send them to orbit, theoretically speaking, the satellite can stay there for a very long time. Unless some circuit burn or you got some solar flare or some anomalies, satellite should be able to stay here for years and years and years because it's a very stable position. And you may be looking at this picture and go like, Miss, I remember this one is the first type of gravitational question that I did where the gravitational force provides the centripetal force. Well, if you're thinking about that, good job. You're physicsing, you're doing your physics well. You have the main ideas down. So in this question, we're going to take a look at this again. But what we're going to do is instead of looking at forces, we're going to look at energy. Okay, so I'm going to just park this here. Okay, let's go. Why are the fonts so small? But let's go. The Earth may be considered as an isolated uniform sphere, sure, with the mass m concentrated at the center. This is usual. Show the kinetic energy of the satellite is given by this expression, where g is the gravitational constant. Explain your working. Okay, my friend, you look at this satellite. Definitely something is providing the centripetal force. Okay, so you want to think about the kinetic energy, right? Always think from the perspective of the fact that, number one, this satellite is traveling in a circle. Your gravitational force provides the centripetal force. Because if I want to find kinetic energy, I'm going to use the equation of half mv squared, right? And this ms is the mass of the satellite. So I'm going to write ms here. And this is big M. So this will be ms. I have the half already, 1/2. I have the ms. So when I see this gm/x, it tells me I need to substitute my velocity. I need to be able to substitute this v. Because there's no v in this EK equation. What v are we talking about, my friend? Well, we're talking about the tangential speed. So the satellite will have a tangential speed. This is my v. Okay, it's the same v as half mv squared. Okay, so let's try to find v. We can write v in the expression of gmm, by thinking about centripetal force. So this is a two-step process. Step 1. Centripetal force is provided by gravitational force. So I'm going to use mv squared over, okay, wait first, the orbit radius is x, so mv squared over x. Normally we use r, but today they decide to just switch things up a bit and they let this one be x. Okay, x law. And this is a gravitational attraction between the planet, so that will be G, capital M, and the satellite ms. So I'm going to put ms here and ms here. Okay, over x squared. So this one is a little bit strange, but hopefully the equation is not too unfamiliar with you. The process is not as well. First things first, I will cancel off the like term. So ms can cancel, ms can cancel. Okay, and what do we have left? Oh, wait. This x also can cancel. Good job. Oh, we got v squared already. What is v squared? V squared is gm over x. Beautiful. Now we can move on to step 2. Kinetic energy is equal to half mv squared. but this is ms. So I can write half ms. We have v squared, teacher. Yes, we have v squared. Very nice. I like this. All right, so in the end, what do we get? We can bring this together and think we have our answer. G, mass of the planet, mass of the satellite, over 2x. Proven. So where are the marks? 1 mark when you use centripetal force is equal to gravitational force. And then you find the expression for v squared. 1 mark if you substitute into the half mv squared equation. And then the correct substitution, the steps make sense, leading to the final answer. Okay. Okay, so after examining the mark scheme, 1 mark is for this statement, gravitational force is provided by centripetal force. Or, I guess, if you write this sentence, it'll be okay lah. Writing the statement is nicer. Okay, but this is also okay. So, and then substituting the right centripetal force and gravitational force equation is 1 mark. Clear algebra. This one, this equation plus clear algebra substitution. So I should be able to follow your working to understand what you did here. Like, oh, there's v squared here, and you substitute v squared here. There. V squared is here, gm over x, you substitute here. So I should be able to see as someone who is marking. You started from centripetal force. So you're telling a story using equation. You started from centripetal force is provided by gravitational force of your satellite. And then you use the expression for centripetal force on one side, gravitational force on the other side. That will be the second mark. Once you find v or v squared, you can substitute inside here to get this one. So if I see that movement, that will be the third mark. All right. Okay. Next one. Actually, this is M mark. Okay lah. Does it matter? If you like to skip steps, then it matters because you want to know which one you can skip and which one you cannot skip, right? So let me explain a bit to you if you don't know this. This is A1 actually. Okay, so like that. B1, B marks are free. If I see this, I give you 1 mark. If I don't see this, I don't give you 1 mark. Straightforward, okay? So it's possible for you to get B1. Maybe you don't know how to do M0, A0. Okay. It is also possible for you to get B0 because you didn't write the explanation and you like to skip steps. But at least you show the centripetal force equations and the gravitational force equation and equate them. And there's clear algebraic substitution. So that would be M1, A1. Of course, it's possible for you to get full mark lah, B1, M1, A1. Okay. Or you could get B1. This one is not possible. Okay, so in other words, right, the possible way of marking, the possible marks that a candidate can score is either all 0 or 2 marks because they managed to show the substitution correctly, or 1 mark because they explain but they don't know how to do later, or full mark, or 0 mark. Or sometimes, rarely, we get this lah, but this is also possible. Meaning somewhere here something went wrong. But this is the last leg of the race. Normally, we won't expect anything wrong to happen here. So anyway, basically, you must get M mark to get A mark. If you don't get M mark, you will not get the A mark. Okay, your method is insufficient, so your answer is not valid. Method insufficient, answer not valid. Method sufficient, but on the way to the answer, unsure what happened. Copy error, transfer error. All right. Okay, part 2, state and expression. Okay, this one no need to derive. We just write the expression. In terms of gm, mass of the satellite, and x, the potential energy of the satellite. Okay, so we know potential energy. It is negative g m over r, but I'm just going to use their values now, ms over x. So I'm going to write here the equation for you. Negative g m over r. This is the format that we are used to, but now we have to put in their values. Okay, must put negative. Yes. Negative compulsory. Why? Because you are defining something. You are not looking for change, my friend. You're asking to write an expression for potential energy, and potential energy is always negative because it's an attractive field. So it's like very basic things that you should know about gravity. Potential energy is always negative. Anyway, using all the things that you have found just now, derive an expression for total energy. Okay, this is easy because if I want to look for total energy, I will just take potential energy plus kinetic energy. So what's my potential energy? Negative G m ms over x. And what is my kinetic energy? I have derived just now this one. G m ms over 2x. Okay, so I will factorize, I guess, or you can look at it this way lah. This is a common factor, gmms over x. So what I have is actually negative 1 plus half. What is negative 1 plus half? Negative half lor. So you can actually just put negative 1 over 2 bracket g m ms over x. Okay, or you slowly factorize lah. It doesn't matter. I skip one step because I don't have space. Okay, so what I did was I saw that this gmms is the same, gmms over x is the same. So what I have here, the coefficient is negative 1 plus 1 over 2. So negative 1 plus 1 over 2 is negative half. Is the negative important? Of course. Negative half gmms over x. So this question, right, is all about derivation and explanation. There's no calculation here because in part B, it says a small resistive force acting on the satellite causes the radius of the circular orbit to change. Interesting. Using your answers in A to state for the satellite whether each of the following quantities increase, decrease, or remains constant. Okay, so let's pause a bit and think. Whenever there's small resistive forces, this is energy lost to heat. Energy that you cannot get back. Energy that you can get back is like, for example, you throw a ball away from you upwards. Energy that can return to you. Let's say you throw a ball upwards. Yeah, the ball is losing kinetic energy, but it's gaining potential energy. And eventually the ball will return back to you, to your hand, and you get back the kinetic energy. But if there is energy lost to friction, it doesn't come back anymore. You can't transfer heat loss or heat of friction to kinetic energy or to potential energy of the object. Particle cannot, object cannot. So in this case, the total energy will decrease. Decreases. Okay? Because the small resistive force, so there is energy loss. All right, radius of the orbit. Okay, there are two ways to do this. I'm going to use the mathematics way because we have an expression for total energy. What is my total energy? Negative. Can I draw a graph? Can. Let's do that. Let's draw a graph of total energy against distance, radius of the orbit. Okay, we're back. So you see, I got the planet and the satellite there already. Okay, S is a satellite. So here, right, currently, this is the value of X. Okay, so we're going to measure X. I mean, this D, so it's your X lah. Okay, so let's think about our kinetic energy. Kinetic energy has a inverse relationship with distance, X. So as the distance increase, the kinetic energy will decrease. This is positive number, so this is not a problem. Okay, so kinetic energy is going to start from maybe here, and then decrease lor, until eventually it reaches 0 lah, but it's not the problem here. So at this point, or at any point here, this EK is equal to positive G mms over 2x. Now what about potential? Interestingly, potential is double. This is half, this is 1, but negative half. Okay, boss. So negative half means you better double this. And your potential will be something like this. Okay, so this potential, negative G mms over x. And if I add the blue graph and the red graph, I will get the purple graph, negative. So right now, this is the value of my x. I'm gonna sketch it out for you. Here to here is my x, but the total energy decreases. Okay, so this purple graph here is total energy, negative G ms over 2x. So if my total energy decrease, it means that this energy against distance graph, it is pretty obvious that my satellite here, if the total energy is going to decrease, it has to go closer. So a satellite has to travel down. Does that make sense? So you want the total energy to decrease, to be a bigger negative number. So if decrease, then what happens to your x? Your x will be less. So the radius actually decreases. Okay? So I repeat, it's a negative number. You draw out the graph, no? If I want my satellite to lose energy, because this is negative, it needs to be a bigger negative number, meaning x have to be a smaller number. Or you can sketch out this graph. Lose energy means I need to slide down the curve. To slide down the curve, my x has to decrease. X has to decrease as you slide down to show a decrease in total energy. Why is there a decrease in total energy? Because of our good friend resistance. Okay, so because of this, we can say the radius decreases. Okay, so we know the radius decrease. We know that this orbit will shift from the original position to, let's say, this new position here. So this is my new orbit-ish. Okay, so it's gonna move closer. So what happens to the potential and kinetic energy? Okay, let's check out potential energy first. Potential energy is also negative. So following the trend, if we move from here to here, your total energy decrease, your potential energy also decrease. So that will be decrease because of the negative number. You make x smaller, the negative number become more negative. So potential energy decreases. What about kinetic energy? Well, my friend, if I continue the kinetic energy curve like that, okay? So here you can see that if I move from here to here, the kinetic energy actually increases. You're traveling from here to here. Ke increases because when the value of x is smaller, it becomes a bigger positive number. Bigger positive number means bigger value, no? Increase. So from here, Ke increases. Okay, I'm going to zoom out a bit for you. So the whole idea here is to sketch the graph. The question starts off with what happens when there's resistive forces. Review the question. When there's resistive forces, the total energy has to drop because you are losing energy. So if the total energy drop, if you look at a total energy graph, it is negative. So when the total energy drop, it should be a bigger negative number. To get a bigger negative number, x has to decrease. Or you look at the curve of the graph, you want this to drop. If it goes in the opposite direction, then total energy will increase. But here your total energy is decreasing. Okay? And then when we know that the x is decreasing, this is the important point. So step 1, we found out that the total energy decrease. Step 2, we found that the radius decrease. Because we know the radius decrease, due to the total energy decrease, which decreased due to the resistance or air resistance or the resistive forces. Then we know due to the decrease in the orbital radius, number one, the potential will also decrease because you are moving closer to the surface of the planet. And you would naturally also move faster, so your kinetic energy will increase, or you refer to the graph, or you refer to the number. If I make x smaller, this will be a bigger negative number, so potential energy drop low. -10 is smaller than -8, okay? This x here is a smaller number, cause radius decrease. This EK is a bigger positive number. +10 is bigger than +8, okay? So it's the positive negative sign issue that can be a bit confusing. So draw a graph to help yourself if you need. And if you want to, I can show you this graph. Okay. So here you can see the total energy and the potential energy and the distance from the planet. Okay. So let's say I bring the distance closer. Now, when I bring the distance closer, I'm sliding down. The potential energy is decreasing. The kinetic energy is increasing. So as I decrease, you can see a satellite is moving so fast. Spin, spin, spin. If I increase the distance, the satellite will slow down. That's the only observable one that you can see unless you draw the graph. Okay, so pro tip here is be familiar with the graph such that when question asks you statements like this one, when they ask statements, you can just visualize the graph or do a small sketch here quickly and decide what are the changes. Okay, so just as a bonus, I'm going to write down a brief explanation. Okay, so total energy decreases due to energy loss to resistive forces. Okay, radius of the orbit decreases because total energy is negative. ET is equal to negative GMMS over 2x. Okay. Potential energy decrease also because potential energy is negative. Always negative, actually. Always. Always. Okay. And kinetic energy increases because kinetic energy is always positive for a satellite in orbit. Okay, so always think about the fact that at the end of the day, you and I, our total energy is negative. We owe the Earth an energy debt. Okay, you can Google that. There's a very good Kuskazat video around that. Okay, but our total energy is always negative because once upon a time, when the universe or when the solar system was formed, all the particles that made up your body was drawn to planet Earth by the gravitational field of the Earth. If you want to run away from the Earth, can repay the energy. Repay this energy debt. Okay? So if you want to escape, let's say you want to hop on a rocket and travel away, we need to have more. So now your total energy of the rocket is very less. Maybe your rocket now is traveling, it doesn't have enough fuel. So can it travel away from the Earth? Nope. It will reach here and run out of energy. So if I want the rocket to escape, I need to give it enough energy to travel to infinity. Okay, let's give it more. We escape the planet's gravitational potential. But currently, if let's say you don't do anything, you turn off you stay in orbit, you don't have extra energy, your total energy is negative, we cannot travel away. We'll get stuck here. If I increase the total energy, then we can travel further, but we get stuck here. Increase the total energy a bit, travel further, but you need to make it positive. Then we will escape the planet's gravitational field. So this is what this negative potential means. It means that the satellite is stuck in the well and it's rotating here because it doesn't have enough energy. It is stuck rotating and orbiting around the planet. You want it to run away? Can. You need to give it more energy so that it can whee. That's what the negative implies. That's why this 2 is always negative. Always negative. Anyway, this 3 is for satellite in orbit. Not for all cases. Please look at the case by case. You rocket running away, of course, this thing won't happen now, okay? Satellite in orbit. The explanation is valid for the satellite in orbit. Okay, that's it for this quite challenging question. So orbital mechanics, aka rocket science. Take some time to digest this, and I'll see you in the next example video. Bye-bye.